calculus, by the way. If you look at Newton's original book, it's written in Euclidean geometry, and no one could understand it. And it was only after continental mathematicians translated it into Leibnizian calculus that Newton convinced, that people were convinced on the continent that Newton was right. So, but anyway, so let's take another example. I have a physicist friend who unfortunately is gone at IBM, Rolf Landauer, and he would always tell me practically every time we met in the halls, real numbers don't exist. He would say no measurement was ever made with more than, I think it's 15 or 20 digits of precision. Okay, I used to think very skeptically when I heard him say that. But think about the Heisenberg uncertainty principle. According to the Heisenberg uncertainty principle, it has to do with why atom smashers are so expensive that we can't afford them anymore. You have the best one in the world at CERN, and the US wanted to do better, of course, but they ran out of money. And why do you need money? Well, to look at things smaller and smaller, you need higher and higher energy, according to the Heisenberg uncertainty principle. So to get infinite precision would need infinite energy. So why is there any reason to believe that infinite precision exists, right? So another example of course, there is the notion of atoms, right, which are discrete rather than continuous, but quantum mechanics plays it both ways, right? Because they talk about particle-wave duality. So on the one hand, it's discrete, but on the other hand, they're talking about continuity. So they're sort of hedging their bets. But nevertheless, there is this strong suggestion coming from quantum mechanics, even though the Schrödinger equation is a partial differential equation, that there is discreteness. It's the discrete spectrum, right, of energy levels, right, for example, of the hydrogen atom. So there's some new stuff going in the direction of discrete physics. There is, for example, let me give you an example. Well, there's a small detail that quantum mechanics and general relativity contradict each other, right? Quantum field theory, let me tell you sort of why in kindergarten explanation, because I don't really understand quantum field theory and general relativity very well. But you know that the quantum field theory view of the vacuum is that a vacuum is full of activity, virtual particle pairs being formed and annihilating each other. You get this creation of a particle and an antiparticle, and then they disappear, they recombine. And it's okay as long as you think this violates conservation of energy, right? Creation of matter out of nothing, and then it disappears. Well, it doesn't as long as Heisenberg uncertainty principle isn't violated. So the idea is, if the product of the energy of the particles times the amount of time they exist is of the order of Planck's constants, it is okay. So the idea is that there are virtual, normally it's an electron and a positron, right? A negative and positive electron being formed as a pair and annihilating each other, which explains quantum electrodynamics. But there also, according to the quantum field theory, are these virtual elephants and anti-elephants being formed. They last less than an electron and an anti-electron before they recombine. And unfortunately, elephant is very light. There's some small probability of getting an enormously massive thing, say maybe the mass of the sun, and an anti-thing created, and briefly. And the problem is you can get so much mass that you would get, according to general relativity, a black hole. You would get space-time collapsing. And so, if this view is correct, then space-time becomes a problem because the topology would be changing constantly because you would be getting these virtual black holes forming all the time. And nobody knows how to deal with it. In fact, they think it's probably wrong. So the one way out of this is this crazy theory called superstring theory, which now is called, I don't know, brain theory or something. And the reason for superstring theory, they may not confess, is the problem that quantum field theory and general relativity contradict each other. And what they want to do is have a quantum theory of gravity in string theory. So how do you do it? What you have to do is avoid arbitrarily small distances. I'm arguing that arbitrarily small distances don't work, that you get divergences and infinities in many places in physics because of arbitrarily small distances. It's just that physicists are very good at not asking the wrong question. Mathematicians, you're in trouble in a math theory, right, if there's a contradiction, if a calculation gives infinity, but physicists don't care. They just learn not to ask the question. So what does string theory do? That's why you don't talk about the energy of a point electron in the field around a point electron. It's infinite. It's even infinite in quantum electrodynamics, according to Feynman, but I don't understand the detail. So what happens with this string theory? String theory needs a minimum distance scale. That's how it avoids the divergences as you go to arbitrarily small distances. And the minimum distance scale is the loop of a string. Too bad we don't have windows here. Isn't this awful? It's dark. There's no air, and outside it's a beautiful day, and I come from where there's snow, and I love it, and we're trapped in this coffin. Oh, well, I'm sorry. So string theory is the idea of putting a minimum distance so you don't go to arbitrarily small distances. Now, another problem is the quantum vacuum. I understand, I have to check up on this because I'm not a physicist. I understand also that the quantum vacuum has infinite energy if you do the calculation, according to quantum field theory. And, physicists sort of finesse the problem. They don't want to admit their embarrassment at the fact that the energy of a vacuum is infinite according to quantum field theory with the virtual particles forming all the time. So what they do is they calculate differences. The ground energy of the vacuum is infinite, so you calculate the difference between the vacuum energy and the energy of some other situation, and then you get a finite answer, fortunately, so they don't care that the equations gave them infinity. But I think there's a problem, right? And mathematicians tend to get annoyed when something diverges, right? So I'm telling you that there are some reasons in physics that physicists don't want to talk about, but every now and then, as I attempted to be an armchair physicist, I would notice that there's some calculation which gives infinity, and physicists say, okay, that means we shouldn't do this calculation, and they go on. But I began to feel, that there was something wrong with real numbers. Now, there is a new theory which is becoming popular. It comes from black hole thermodynamics, and it would be nice if we knew there were black holes. Black holes depend on general relativity being correct for enormously high field strengths, and most physical theories don't work if you extrapolate them orders and orders of magnitude. But let's assume that the general relativity is correct and that black holes actually exist. I don't know, right? There isn't very good physical evidence for general relativity because it's very difficult to do experiments. But anyway, if you follow this, if you believe in this theory, it can be extrapolated to those ranges. There's a thing called the Bekenstein bound having to do with the thermodynamics of a black hole. And this is related to stuff that Stephen Hawking did in England. And Bekenstein got this bound on the amount of energy, on the entropy of a, well, actually it was the entropy of a black hole originally. But Bekenstein has extended it. And I think the argument, I'm probably wrong, goes something like this. If you could get too much information, the question is to put a bound on the amount of information in a space-time cube and show that there are a finite number of bits of information there. And the way it sort of works, I have no idea if what I'm saying is right, but if someone is a physicist, maybe they can correct me afterwards. It's sort of like this. I would guess that according to the Heisenberg uncertainty principle, if you want to get a lot of information inside, you have to go to very high energies because of the problem of making measurements very precise needs high energy, according to the uncertainty principle. And if you have very high energy in a small amount of space, you get a gravitational collapse. So Bekenstein takes arguments of black holes and generalizes them and says any little physical system has only a finite number of bits of information, very large, but only finite. And lately there's been some people like 't Hooft, is he from the Netherlands, who has taken this Bekenstein bound and made it into a very general principle called the holographic principle. That there's been a fair amount of discussion. Hot in here, isn't it? The holographic, maybe I'm talking too fast. The holographic principle says that a physical system, any physical system, I think this comes from the Bekenstein bound, but it says taking this Bekenstein idea and generalizing it in some directions. We don't know if the physical universe believes in it, but mathematically there's some arguments for it. You can find that a physical system has a finite amount of information, of zeros and ones, of discrete information in it, and that this information grows as the event horizon of a black hole, that is to say, as the surface area of the physical system, not as the volume, which is very, very strange. So it looks like a holographic projection onto a plane of a three-dimensional system, and it looks like it's saying in some sense maybe things are really two-dimensional instead of three-dimensional. There's some discussion of this lately by some physicists. It's really very interesting. So I'm trying to give you all these arguments. Now, coming from traditional physics, saying that maybe there's